Okay, recording. So we read chapters 3 and 4. It started with bag of words, kind of the count vectorizer stuff, and then it talked about in chapter 4 the TF-IDF and stuff like that. Did anyone have any questions to start us off? Anything you were unclear about?
So I don't, this is kind of later in chapter 3, but they went over the likelihood ratio. And I was wondering if anyone had a good concept of that, because they kind of just rushed over the math and I didn't look any further into it, but more of a layman's term explanation of how that's used within, I guess, bag of words. That's on page 55.
Mm-hmm. Yeah. So what they're essentially saying is, what is the probability of two words randomly occurring just because they're common words versus what is the increased likelihood of a word occurring after because those words go together. Does that make sense? So if you have the word the, a lot of words are going to happen after it because that's just such a common word. But you're looking for a word that happens more frequently than normal. So if you have like the ball, the cat, there's probably certain words that are more likely to come after it than like the something else, some other word that doesn't fit in that scenario.
Like
So
the
you're,
end.
yeah, yeah. Um, So you're looking for something that occurs more often than just random chance, and you have to factor in the relative probabilities of it, right? Because the zebra is probably not going to occur very often just because zebra isn't that common of a word. Um, so that's the gist of what that equation is saying, is you're trying to factor in the probabilities of all of those different scenarios.
But they're, so from what I understand from the text, so they're saying that the collocation of more frequently or more probabilistic n-gram words, that represents a collocation.
Mm-hmm. Yeah, so an example of one of those would be like New York or something like that. So those words very commonly go together because it's a pair that a lot of people use. So you might want a specific spot in your index that's just for the pair New York, because that means something different than new and York as separate words. So
Yeah,
you're looking, go
so
ahead.
I wasn't so sure about the math. Like if you just had two words and if they were both really common words, I don't even know, you know, the and I or whatever, right? So if it was just two words and if the and I are like 10% likelihood, then having the two next to each other would be like you just multiply those probabilities. It'd be, you know, 0.1 times 0.1, so it'd be like 1%, right? But I guess the math's a little bit different if you're talking about a 5,000 word chapter and you've got lots of bigrams, then what is the chance of having like those two words next to each other? It's not just 1% at that point. It's actually going to be higher than that because since you've got so many bigrams, there's more opportunity for the two to happen to. But in that particular case, the and I probably in real English fall next to each other quite rarely compared to the fact that they're super common words. And so that would be the opposite of a collocation, right? That would be this does not seem to be its own named entity, you know, right? Whereas New York or maybe neural network, right? I mean, neither of those words might be super duper common, but together they're just like way more common than just the frequency of the words alone would normally imply. So then maybe you want a bigram neural network to be in your vocabulary.
That makes sense. Cool. Thank you for the explanation.
And I have a question. I don't know if it makes sense or not, but I will ask it anyway. So given the kind of a lot of discussions the group has done for birds, and given the advancement of that, how useful is n-grams, like using the approach of some of these things that they talk about in the chapter 3, I think.
I would say not as useful. It is definitely useful when you want something that's interpretable and you can look at the results and kind of inspect what's going on. And it might be useful. I don't know. The old methodology might have said, oh, it might be useful if you have not a ton of data, but that has kind of changed with BERT because BERT is able to handle smaller amounts of data too.
Yeah. I would throw out that maybe it depends on the task. So for example, I was listening to a talk about clinical named entity recognition. And it's not necessarily about bigrams per se, but basically, you know, if you have a bigram like breast cancer, it's 2 separate words, right? It's super important that the model understand that breast cancer is a thing that's distinct from the 2 separate words, right? And so so I don't know if that exactly fits with your question, but so if you're trying to, you know, like that contest where, you know, we're talking about like whether something's toxic or not, you know, like you don't necessarily need to know what the individual words mean. You're just trying to look for the whole sum of what's going on. But if you're trying to do something like understand a doctor's note, then I think that's a different kind of a problem because you're then looking to pull out specifics from it.
Gotcha. So a follow-up question on that is that if like in BERT, what will be considered as the features? Is there a way to extract features?
So the input into BERT, just to understand the inputs and the outputs, the inputs is the indexes of the word pieces. So it will take all the words, it will chunk them up into subword pieces. So it might be, I guess like biology or something like that. It might grab bio and ology, and then it has those 2 pieces. It passes those in. It knows about those subword pieces, and then its output at the end could be directly a prediction, or you can grab one of the intermediate layers and it can be a vector. So it can output 768 numbers, and that's its understanding of the text that you passed it. So those in theory could be features in the sense that you pass them into the model. But BERT on its own is not, it can just be directly used to make a prediction. It doesn't necessarily generate features. It takes the index of the subword pieces, and those are its features, basically.
Gotcha. Okay.
Yeah. So in that particular case, BERT has moved away from whole word vocabulary. So its tokenization uses pieces.
Right. Thank you.
And so in that case, just to follow up, what do dimensions mean with embeddings? I mean, from this chapter, it looks like dimensions are basically just the words, number of words themselves, like one word is a dimension. So in the case of BERT, is it like one subword is a dimension?
Not necessarily. So it's different depending on the model. So BERT is configured to take in 512 subword pieces at maximum, and then it creates an embedding for every single one of those words. And the size of the embedding, the number of dimensions, is just arbitrarily defined. They just tried various different dimensionalities and they found that 768 was very successful. So they have a 768 dimension embedding for every single word, and then at the end you can do various different aggregations or linear combinations of them in order to condense that meaning down and make a prediction with them. But the dimensions is just arbitrary. It's not linked to the number of words or the number of tokens you're passing it or anything like that. It's just enough dimensionality for them to capture the meaning that they want.
Yeah.
So
Okay. So I was gonna say with like some examples in collaborative filtering, I've seen dimensions take on some pretty magical properties. Like in one of the fast AI lessons, so we are not really actually encoding this information, but after training, we find out that, for example, in a recommender system, we are finding movies are automatically there is a dimension that speaks of whether a movie is really campy. There's some there's one that speaks of whether it's very violent and stuff like that, which automatically happens just with the data. So are those the kinds of dimensions we're speaking of here that capture, like, I guess in this case, context and meaning and such?
Yeah, so what I was going to say is you could do an interesting experiment and you could look at certain dimensions that have very high positive and very high negative, large negative, whatever,
Value.
very negative values. And you could say, hey, isn't this really interesting that like dogs and cats and other animals have very large positive values in this dimension, right? And books and rocks and, you know, astronomical
Mm,
terms have very large negatives. So this seems to be sort of a, you know, animate, inanimate dimension or whatever. And so
mhm.
you can kind of do it kind of like you're talking about, a fun thing to look at them. But at the end of the day, that's just us trying to, you know, interpret and understand, and it's not necessarily.
There's a better way to do it that involves not any of the one individual dimensions, because any particular concept or thought is going to be spread across many different dimensions. Like the fact that it's a movie, the fact that it's campy, the fact that it's funny, the fact that it's, you know, confrontational or whatever. All of those will be and all spread out throughout the dimensions, and you're not going to be able to isolate. None of the dimensions mean anything at the highest positive level in isolation. They can only be combined with others, and the zero values as well as the half, the max values as well as the max values all over the place. It's some odd profile that means a particular thing. And so what you want to do is just take the embedding for that thing, that concept that you have, and compare its distance to the vector that you're interested in. And it's that distance that defines how much of that ness is in that embedding.
Mm,
So if it's campiness, then you just do the embedding for
mm,
campy or campy movie, and you do the cosine distance with that and whatever thing your text you're looking at, and it will tell
mhm.
you how much campiness, movie campiness there is in that thought. They're like
So
thought
then,
vectors.
so then, uh, does BERT also provide a way of like looking at, or rather, clustering by dimensions so that we
Oh
can
yeah.
interpret? Okay, okay.
You can do this, all the same stuff you can do on any word vector. You can do on the individual word piece embeddings that Ryan was talking about. You can also do it on the entire embedding associated with the entire statement.
Okay.
Again, 764, or you can use the actual sequence of 764 embeddings like an image. So it's like a two-dimensional image of a statement. It generally truncates at the end of, you know, the period, and it's nothing but the class and the emptiness after it, but it's still a two-dimensional thing. You can, the transformer, the really awesome thing about transformers is they output the same object at each layer. So you can apply that same layer over and over and over again. The embeddings on the input are the same as the embeddings on the output in terms of dimensionality and size and everything. So it can be as deep and as complicated as you want.
Going back to the count vectorizer and this stuff out of the book, they talk about some various filtering methods and kind of reducing the dimensionality of that stuff, so you don't kind of just continue to grow larger and larger and larger and have a bunch of words that aren't useful. So one of them was looking at the frequencies of words and filtering out ones that were exceedingly rare. So if you have 100,000 documents and you have a word that only occurs in 3 of them, it's probably not worth it to add another dimension just for a word that's only in 3 of the documents. And on top of that, you probably don't have enough instances of that word to actually extract any signal out of it. So that was the min df that they were talking about, the minimum number of times that it has to occur for it to become a dimension in your count vectorizer.
And that has
And
an
then Ryan,
exponential effect on the size of your vocabulary. So as you go from 2 to 3, you'll cut your vocabulary size in half.
and then Ryan, the flip side of that is you can have a manual list of stop words, but the flip side is if you have a word that appears in 95% of your documents, then it may not really be differentiating anything amongst the documents because it's just always there.
Mm-hmm. Yeah. So you can have a low frequency filter and also a high frequency filter, because if you have, like you were saying, like we already have a stop word list, but if you have the word the or of or something like that, or you have some word that is like all of your documents are memos or something like that, and it says memo as the first word of every single one, that's not a useful feature to differentiate between any of them. So you might want to just remove that as a feature in your vector.
Yeah, I actually have a non-NLP example of that. So so we work with this healthcare cost model that was developed for Medicare. And so these are older people. All right. And so there's things that you expect to be in there, like diabetes, heart issues, and things like that. But one thing that's very much talked about is hypertension. It's actually very important for your health to not have high blood pressure. And hypertension is not in the model simply because such a large percentage of seniors have hypertension that it's actually not very predictive. It's not that helpful because almost everybody has it. Now, in theory, I'm actually slightly surprised that maybe the few people who don't, that it would be a predictor of lower cost. But however, when they built the regression, it actually turned out that it was not predictive. And so it's not an NLP thing, but that's a case where its frequency was just so high that it ended up not being useful.
I would encourage you to actually look at the accuracy lift when you removed it or added it, because I can't imagine that it was 0. But
yeah, I mean, this is the model I built. This is the model that the government, built, and
right.
And I do know for a fact that hypertension was in the original model of like 250 whatever buckets, and they narrowed it down to 70 in the original model. And so they for simplicity, they threw out a lot of things, and somehow hypertension did not make the cut.
When you're looking for explainability, it makes a lot of sense. But personally, I would discourage everyone from ever eliminating stop words arbitrarily, based on any max DF smaller, and that's a max DF of maybe 0.99 I'd be okay with. But anything below that, you're really flirting with some potential statistics that you're losing. People came up with that idea back when all there was naive Bayes and logistic regression on the presence or absence of a word, not the actual total count of the frequencies of the words, and not after being divided by its frequency of the documents in a TF-IDF vector. All of that takes care of that problem of the significance or insignificance of that particular word. And you're losing that stuff like, if there's 10% of the words in a document that are the word of, that's a more grammatical document than one that does not include 10% of the words in that document being of. And so the TF-IDF value gives you a lot of information about the various personality or sentiment, a lot of the things you're looking for in that string, and you lose it as soon as you get rid of it. So you just, at the very least, try it with and without that. If you can afford the extra memory of including one extra word in your vocabulary, just do it and see if it actually helps your model to eliminate it. It never does in my experience. It always hurts your model. Sometimes it hurts it a very small amount. Sometimes it hurts it a lot. And you can't really ever know if you're blind to it.
I think in the book, they make the distinction of the importance of stop words or the non-importance of them based on the kind of task you're doing. So for sentiment analysis, they are important. So you wouldn't want to get rid of them because semantics matter. But in case of like document classification, maybe not as much because they might go the other way.
Yeah, I don't know. I've been schooled very, very often in projects of my own where I've made that mistake. I've never found an opportunity where eliminating them helped. Sometimes it didn't hurt as much as I hoped, but always it hurt. It's just a matter of how much it hurt. There's no problem in which the meaning of words don't matter, unless you have a problem where actually the meaning of the words and the count of the words in a particular sentence just doesn't matter. But even in sentiment analysis or classification, mostly you're classifying documents according to something about the meaning of the words. If that's the case, I don't know.
One of the interesting things that can happen with that, so let's kind of go along with the hypothetical that you have a max DF of 0.99. Let's say that hypertension is in 99%, for example, and we keep it as a feature, and then we compare when we drop it as a feature. In theory, there is a world where hypertension is a perfect predictor, but the most it's able to differentiate is the 1% that does not have hypertension. So it could, in theory, be a free 1% accuracy boost, but you drop it because it looks so frequent, potentially. That's just a hypothetical scenario that could happen. But the most it could ever impact is 1%, in theory.
Exactly. So you're putting a ceiling on the maximum harm you're doing by eliminating stop words if you set it really high.
Okay, so related to all that, this chapter comes through with the filtering, with the n-grams, with stemming. So it looks like it's heading towards a progression of understanding words better and better, but it doesn't get to semantic networks. And I'm thinking BERT with its deep learning, maybe in that deep bucket somewhere, it's got its own semantic network that it's come up with, but English is a relatively fixed language and there are authentic word semantic networks. Why aren't they used?
There are sometimes used to create those embeddings, but it's just more accurate to create the embeddings straight from the text. So
the thing is that now with BERT, you've just got so much data to throw at it to train it. When you train it on Wikipedia dumps, you don't really need that tagging of like, what's a verb, what's a noun, because you just have so much data. But before these things were really, like before the massive transformers, that's where it really helped tagging your text and whatnot. But it's just not as needed anymore, just due to the size of data it's straight on.
Yeah, I'm not talking about noun verb types of thing. I'm talking about like semantic networks, those really pretty globes of all of these, king, queen versus, where it's
like
the actual
WordNet?
meanings of the word. Yeah.
WordNet on where it's like Princeton, I guess, has that WordNet network. Is that the one?
And is that based on a semantic network where it's words?
No, that was handcrafted. That was handcrafted based on the definitions of words. But if you compare it to the semantic network that you can create based on the embeddings you get out of Word2Vec or BERT, the network you create based on the distances between those vectors looks out very similar to that one you have in WordNet. And you can go the other way around. You can take that WordNet and you can turn it into embeddings. And people have done that as well and compare their accuracy. And they find that the working directly with the text, that the definitions don't capture all of the connotations of words. They don't capture all of the ways that words are used, and they can't keep up with the way words are evolving. And that handcrafting just can't keep up with the way words are actually used in the real world.
So I don't know if this is taking us a little bit far afield of the chapter, but like Word2Vec was, those embeddings were built looking at words that are near each other. And BERT uses, as part of its training, a masked language model where it's basically looking at the words near. I know BERT also can look at words that are sort of far, but it's looking at the words that are near the masked word to predict. So would it be fair to say that BERT probably inherently has the same capability as like a Word2Vec embedding of words as part of what it's doing, its architecture?
Yes. Indeed. It's just much
I
more
think
accurate.
with the attention, it's just like Word2Vec might be able to find similar words, but the thing is with attention mechanisms, you can look at things that are far away. So
Right.
let's say where you have a sentence that's like the ball is round, it bounced 3 times. Word2Vec isn't going to understand the word it there, even though it's referring to ball, whereas attention would be able to draw that connection. So that's kind of the distinction between the two there.
Yeah. But what I'm trying to get at is, you know, I think you could make the argument it would be redundant if you used Word2Vec embeddings to try to boost the, you know, BERT instead of just giving it the plain words or word pieces.
Right.
I'm actually
So
not.
then my quick question is just so fundamentally, I always have this question, like given the availability of birds, do we really still need to care so much about some of the stuff talked about in the chapter? Like to Ryan's earlier point, yeah, if you want to have more like explanation of the model, it seems like it's a good thing to pay attention to those things, but then in the end, it may not be always needed.
I feel like
think,
it's always good to know those fundamentals. Like even like I've built custom transformer models, and knowing what TF-IDF is really useful. You know, when you read a lot of the papers, they still break down like everything is kind of custom written, all their functions. So to understand what's going on, it's really essential to have a solid understanding of what all these terms are and how they work.
And there's a
Just from
really
that sense. But go ahead.
sorry, there's a really important use for all of this that you're learning about stemming and TF-IDFs and tokenization and all that stuff, and that's search. It turns out that these big high dimensional vectors, if we could do a search of the internet for semantic vectors, then that's what we'd be doing, but you can't. It takes too long to do that vector comparison against that vector against all the web pages in the world. Whereas it takes constant time to do that comparison on the presence or absence of words or n-grams or trigrams or charactergrams or whatever you're looking for, because that's a binary vector. And there are all sorts of binary trees and KD trees and ways of indexing that so you can go there in constant time. Whereas with any other approach using actual continuous vectors that capture all of the meaning, you'd be waiting around to the end of the universe to find that page.
And there's also a curse of dimensionality where as much as you can have huge dimensions to represent stuff, you still lose a lot with, like, it's harder to do semantic search when you have such large dimensions. So there's just other issues that pop up too. You can't even visualize it the same. So as much as there is PCA and all that stuff in TSNE, it's still, you're still at some point going to have to like condense down your huge features to lower representations. That's still done pretty often. And there are issues when it comes to search and whatnot for large dimensions.
It's just a fundamental barrier in math. And
Yeah.
the only way to get past it is with this technology.
I would also say that there's a certain level of you have to build something that you're able to deploy and use without unnecessary cost. So if you're building something simple, you don't want to use the 1.5 billion weights of BERT extra large, whatever the flavor of the day is, if you can do almost exactly as well with a simple TF-IDF that doesn't require a whole server farm to run. That's one of the major advantages.
And the explainability issue also comes into play if you have some legal requirement to be able to explain how your model made its decision. Like if you're processing loan applications or you're processing a legal contract or something, or you're monitoring the test ban treaty on nuclear test bans. Sometimes you do need something that has deterministic logic that you can explain in order to justify the decisions that your algorithms are making.
So this isn't really a question, this is more of just a comment, but there were diagrams in chapter 3 that show sort of the feature space, the document space. And so it's like, hey, you know, the word cat, whatever, you know, appears once, and so you see like a data point at 1 on the x-axis or whatever. And then at the very end of the chapter, if I remember right, they talk about, well, instead of looking at this graphically, we could have just represented this as a table, where each feature is a column and each word, has a column, and each sentence is a row. And I did not find those diagrams to be very helpful. I don't know how other people felt. Like I could have been fine if they had just done a tabular representation of their small examples. The dog is cute, the cat is cute, whatever, instead of trying to do pictures. But I don't know if there's some people where the pictures were much better than just having a tabular thing.
For me, actually, this cropped up again. I mean, it was in chapter 2, the whole feature space versus data space, and the same example was shown here also. And I still am struggling with understanding the value of trying to represent it in these two different ways. Like, I don't know what extra information or that we are gleaning with representing things different ways. Yeah. So I'm stuck at a more basic level than you.
Ted, you're talking about the XYZ axis representation of it?
Yeah. So like at page 44 and 45, they have some representations. And for me, if they had actually just shown like a little table with like a column says, the word dog appears, the column for, the word cat appears, and they have ones and zeros, like that to me would have been just as informative and probably for me personally more easy to understand than these visualizations.
So I appreciated it. I think what they were trying to get at visually was just dimensionality. So it's like, here's a 2D, here's a 3D, expand your mind.
Okay, cool.
N-dimensional, expand your mind. But it's like they start you with tiny step A, tiny step B, and then you can launch out on your own. So I at least appreciated the attempt at that.
Okay.
I typically, if we had whiteboards and stuff at the sandbox, I would be drawing this out, and I would be showing the various different ways that we can represent text on the different dimensions. So the way I typically show it is, we've already looked at count vectorizer and TF-IDF, so this is going to seem rudimentary to you guys, but just solving the problem of how do you represent text as numbers that can go into a system. You have to think about like what are the obvious ways to do that. One obvious way to do that might be, let's just give every vocabulary, every word gets its own index. So the is 1, it is 2, of is 3. And if you lay that all out on a number line, you can see that it's showing relationships that you don't actually want. You don't actually want the to be similar to of. You don't want ball to be right next to whatever random word it's next to, because you're showing the model that those are similar because they're next to each other, but you don't actually want that. And so the count vectorizer and expanding to more and more dimensions is telling you essentially that all of the words are equally dissimilar. They each get their own dimension. They're all the same distance away from each other. And then once we step up to word to vec and BERT and stuff like that, we start saying, well, not all words are completely dissimilar to each other. Some of them are actually closer to each other. So we have these more advanced representations that can say, okay, cat is close to dog and things like that. So we can start condensing it and saying not all words are dissimilar. Some of them actually have some similarities, and we can find those similarities.
Thanks, Ryan. I like that.
So yeah, go ahead.
Yeah, a way to think about it is also just like over time how it got more complicated. So as you explained, there was kind of that bag of words idea where we don't really have any understanding of what anything is. There's no relation of what's close, what's far, what's similar. After that, there was more of the word to vec approach where you started to get some similarity, but that was still just kind of straightforward. Then we have stuff like glove. Glove is where you have global vector. So words start to look at other things, just more overall approaches, like what words are related. And even in the middle, there was TF-IDF. TF-IDF is great. You have statistical understandings of what words are. So something that's more statistically significant or just shows up more often, it probably has more meaning to it. So we had different representations like that. Problems with that were that there was no issue of continuity. Like it doesn't matter if a word is at the beginning of a sentence or at the end. That's kind of what gloves really solved. So it still has that statistical understanding, but now it also has an idea of what comes first, what comes after, where in the sentence it is. Then when you have BERT, it's just like they took a ton of data, they let it make its own features, and now it understands so much that we don't even know what the 768 dimensions are. It has whatever it's come up with after learning and training for so long. But there was kind of a good period where that TF-IDF was really strong, but it didn't really have any idea of what comes first. There was no order to text. It was just kind of statistical understanding. And then after that, there was glove, word2vec, and then BERT is the one that kind of puts it all together right now. Those are just kind of different ways to represent text and some of the differences between them.
So the table that you were, so there was the 3D visualizations on page 44. And then there was also the visualization on the table on 73. And that one, I think that they actually should have put earlier, showing just the raw counts of the words given some text. So on page 73, it says, it is a puppy. And then they've got ones for all of the words that were present in that sentence and zeros for all of the words that weren't present in that sentence. And then they have a few different rows of that showing if the word's present, it gets a 1. If it's not present, it gets a 0. I think that they should have put that in the first chapter, actually. But that's just how they organized it. The last thing that we haven't touched on from chapter 3 was the chunking and part of speech tagging. I know there's some more advanced systems that make use of those, but I haven't personally found much use in parts of speech tagging in the projects that I've done. Most of the time we kind of leave that to whatever model we're doing to try to figure out those relationships. But I'm sure that there's interesting things that you can do with that.
I still remember the starts with an L, Lakoff, linguist. All of the arguments about tagging noun, speech, verbs, etc., parts of speech types of things, and then the computers coming up with solutions that didn't require tagging by noun, verb, etc. And that was just a humongous blow to the entire linguistics community. Just terrible. That must have been, I don't even know how long ago, probably 10 plus years ago. I don't remember.
So does anybody know, now that we have transformers, has anybody tried to take something like BERT and go backwards and say, okay, I mean, we have encoded the whole meaning of the sentence, but can we actually go back and find something in BERT that lets us tag, this is a noun, this is a verb, or that kind of a thing?
I've seen a couple of blog posts where they go apart the different layers and try to see what layer is doing what and what activation. And then I think someone visualized what's being activated for different types of words and whatnot. It's been a while since I read it, but there are a couple papers like that. I can post them in the Slack something.
And yeah, and the best syntax tree creators that tag all words for those things are based on BERT or a transformer model. The best ones use a transformer.
So people have updated to actually use transformers for those tasks.
Oh yeah.
Okay, cool.
I just remembered that in one of the previous competitions, I read about this technique called word sense disambiguation. And essentially the idea there is you have a word like bank, and bank can mean different things in different contexts. You can mean a bank shot in basketball, you can mean a financial bank, you can mean a river bank, for example. And so the idea is when we're using word to vec, when we're using count vectorizer, when we're using whatever else, we only have one representation of that word. So essentially, when your model's learning something, it's learning the aggregation of all of those different meanings as one token. So in order to understand some difference between them, what you can do is you can do parts of speech tagging and then generate a new token for every combination of parts of speech and word. So you might have bank the verb, you might have bank the noun, you might have bank whatever other scenario. And so you make a new token for each of those, and then the model is able to tell the difference between the different banks and stuff like that. And we actually used that in a competition a while ago. It wasn't unanimously better, but it got a different enough result that it was useful in our ensemble of models.
It's still a partial disambiguation, yeah, because bank, the building, and bank, the river, are both nouns.
Mm-hmm. Yeah, exactly. But it does at least potentially break some of those ties. It's difficult to try to create. One of the things we were looking at is maybe there's some way to try to derive the different. So you look in the dictionary and it's got 5 different definitions. Maybe there's some way to make it try to derive a different one for each definition. But it's difficult to resolve exactly which usage it is in every case. That's probably a harder problem than what we were even trying to predict in the first place.
So I think that's kind of what I was thinking with the semantic net, but that's keeping more than one sentence in mind. Is as you're going through some longer piece of text, you understand that these words that are kind of correlated in this part of the semantic network are the ones that are active. So if you come up with the word bank, then it's going to be over in the economy section more. So it's more likely that it's the building.
Mm-hmm. Yeah.
Does that also apply or address the situation where you have, for example, very negative words, but being used as really like positive in very positive setting, right? So I think in today's world, like in a lot of social media text, I think people tend to use very negative words to describe how excited they are and things like that. So is that being addressed in the techniques that you guys just described, or it's a different thing?
I think that's kind of hard to say. I know people are trying. I can't say definitively that people are successful, but I do think that BERT and the other models like that are definitely better at resolving the sort of global context of things. Karen, go ahead.
If I could add to that, so there was a paper that I read on extractive text summarization with graph-based networks, and they used I think OpenNLP library for a lot of POS tagging, and the tagging that it outputted was like verb, noun, 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 verb, and like it had a ton of different combinations of what it would give you for their features. I think it was a 300-dimensional representation it would give you, but if there's something like that, it should be able to do a pretty good job at figuring out if the same word is being used in a positive or negative context, since you have examples that are labeled, and it would be able to tell, okay, if this word comes between 2 nouns or before an adjective and a noun or something, it would be able to actually see that difference pretty clearly. And I can't imagine that being the same if it's used in a positive versus negative context. So it should be able to see that distinction. And that just kind of comes from, like, as much as we think of pretty simple, like I can probably list off 10 things I would think of, like you just have nouns, verbs, placement, and maybe total text length, where it falls in the document. But when there's systems that output like 300 features, combining all those things, it really does actually pick out cases like that. So it would be able to tell the difference in a positive and negative use of the same word. At least that's kind of what I got from the paper.
One of the interesting competitions that just closed a little while ago was tweet sentiment extraction. And the idea there was we have tweets and they're trying to pull out the actual portion that is indicative of the sentiment, right? So they might have 160 characters, but only 2 of the words are saying like the movie was not good. So you want them to be able to pull out not good, and the rest of it is kind of just irrelevant. And so they were using BERT and various other models there, and they were actually pretty successful at extracting the sentiment out of there, the tokens that indicate the sentiment.
And even n-grams can often capture that thing that you're talking about, Becky, just by having a TF-IDF vectorizer that counts all the n-grams of like 2 and 3 words. Not good versus good. It'll catch that, for instance. Or it was totally awesome, or totally rad, or totally bad, I guess. I don't know. There might be some words that indicate positivity when associated with a negative word.
Isn't colocation the same thing, a better way, because it is actually capturing a meaning that might not be found with individual words, or whereas n-gram is just an arbitrary sequence. Colocation is, and I'm only speaking from my reading of this book. I have no experience with these things. I'm just basing it on what I've read. And so it seems like colocation captures more information than an n-gram, and can help in a context where you're able to decide whether a so-called negative word is actually being used in a different way.
I think when he talks about collocation, he's just talking about the statistical collocation of words in what's called skip grams. And they're essentially an n-gram, but just where you ignore intervening words. But I don't remember that particular part. But.
So I think that there's kind of 2 different angles we can go at that. So one of them is n-grams in the sense of count vectorizer and TF-IDF vectorizer. You might just look at 1 grams, so just 1 word at a time, or you might look at 2 grams or 3 grams. And so the 2 grams is essentially just saying, I'm going to find every collocation that occurs, potentially, with some filtering in there. You might say, I don't want the really rare ones. But the finding of the phrases is being a bit more, or the collocation pairs is a bit more selective than that. So you might say, I just want the 1 grams, but I also want to find some of the collocation phrases. So you might just say, I'm going to add 1,000 of these. So you can end up on the same conclusion, one of them being, let's just grab all of the 2 pairs of words, and one of them being, let's grab the ones that seem to be significant. So you can end up to a similar solution. They might be, it just depends on the scenario exactly. If you have enough data, then just the 2 grams is probably fine. But if you don't have very much data, you might want to just extract out the phrases, the collocation pairs.
Yeah, I mean, I was looking at this specific example of where, because n-gram seems to be sequence based, where you just like, just words like, coming after each other. Whereas the example they quoted for collocation was something like knock door, where it's not like really knock the door, etc., but knock door, just like a couple of words that are adding to a certain meaning, I suppose.
I think that's a skip gram.
Okay.
And so
Yeah.
So skipgram is basically the word-to-vec concept where we have like we're predicting neighbors given a middle word, right? We're predicting the context given a certain word.
you got it.
Okay.
You can go either way. Either you predict the context, either you predict the 5 words before and after, individually, one at a time. So you predict the 2 gram, then you predict the skip gram of 3, then you keep the skip gram of 4, and the skip gram of 5. You keep predicting all of the context, and that gives you a lot of examples. Or you predict the word that you're redacting, the one word in the middle, and so that gives you only one example.
So what's the difference between collocation and skipgram?
I think they're the same. I think it just means collocation simply means a gram, a word that's close to another
in
word.
A context, right? Yeah.
And so n-gram is just a particular way of predicting a particular collocation. Neighbors, essentially.
Yeah.
I think collocation is a bit more broad. Skipgram is like collocation between the whatever skipped words, like skip 3 grams, skip 4 grams, that's collocation between them. But collocation, just in terms of linguistics, can also mean like collocation between nouns, between verbs. It's just a term that says like between two. So there's, I think, 7 or 8 types of collocation, but it's just a term that describes that. Yeah.
So when we're talking about collocation, they're allowing gram to be anything. It can be any thing, any token. Those tags for tokens like noun, verb can also be tokens if you want them to be.
So I guess the question that I have is, there's the theoretical concept of collocation, but given that it's very compute expensive to even attempt it, does anyone actually do it?
It's a whole linguistics thing as well, just analyzing text from a linguistic standpoint. I know that there's like noun, verb, adjective, and all that stuff. They do collocation between all those with each other and analyze text from a linguistic standpoint. It's still done. It's just not as useful for features.
Actually, linguists use it for topics detection. Yes.
Yeah.
Topic analysis.
Yes.
Topic analysis seems good too.
It seems like the linguistics process is more human directed and uses a lot of domain knowledge. And so they can afford focusing on just a few of the words or a few of the topics or a few of the parts of speech, identifying what those things are that they're interested in collocation of. And so they can compute it quite quickly on just that subset of all the possibilities.
As far as I remember, they use latent Dirichlet allocation for this. I taught students from the linguistic department, and I considered in particular topic detection. It was very quickly. It does use some kind of cutting at some point with single decomposition matrix. You can cut the elements on the diagonal, which do not have much value. But it was very quick,
In a sense, byte pair encoding, which is what's used to create sentence pieces in BERT, it's a form of collocation frequency analysis, because it decides what constitutes a collocation of characters that constitutes a token, but based on their frequency. If they don't occur often enough, then they discard it. It's like an n-gram filter based on frequency. On characters.
But at the character level as opposed to the word level.
Exactly. In character. And in the old days, with databases and such, gram meant character. It's like trigram meant 3 characters. When you're doing free text search, all that stuff I was talking about doing search, full text search, grams are characters. Because you want to account for misspellings and catch them and still find that article in your database. Information retrieval is where all this n-gram stuff came from, and lemmatization in order to increase the recall rate. Unfortunately, we can use them both together and now to create a good semantic search. We use the fast one first to filter it down to the 100,000 web pages that you're going to run semantic search on.
I linked the GenSim library, and they have a phrases colocation finder. And that's something I've used in the past that will find collocations for you. And Ted, you were mentioning that it's kind of expensive to run. I've found that that implementation is actually very fast, to the point that it's actually usable even on 200K plus documents. So just something to look at if you're interested in collocations and phrases and stuff like that.
That's great. Thanks, Ryan.
We haven't talked a whole lot about chapter 4. So I think their kind of overarching concept in chapter 4 was that we have count vectorizer, and that's just the raw counts of the words. But then there's also various different ways that we can normalize it. So they showed L2 norming, and then they showed using the inverse document frequency in order to normalize it as well.
So in chapter 4, in one of the boxes for intuition, they say that TF-IDF essentially is making the rare words more important and effectively ignores common words. How does that correlate with what we saw in chapter 3 about the unimportance of rare words, the min-df, max-df discussion?
I think that was a great point that Hobbes was talking about earlier, where he said that's like a great reason to not remove stop words and whatnot, because TF-IDF really takes care of that. Mm-hmm. But some of the things that I've seen similar to the GenSim that Ryan was talking about, other things that will give you their own word representations, they won't always use TF-IDF, they'll just use TF. So TF is just term frequency, and they don't divide it by that inverse document frequency. So inverse document frequency is essentially like if the word if shows up in every document, it's going to be divided by a very large number. It's not going to be as useful. But when you just have term frequency, that has a lot of weight and significance to it. So some of the things that they use will be based off of term frequency, and that's where I see the value in getting rid of it, because it really messes with stuff. But TF-IDF, that's literally what it's doing. It's solving that problem because it divides it by its inverse document frequency.
So going off of that, I would say that when you're using TF-IDF, eliminating the vocab so the max DF, the frequent stuff, becomes unimportant because it's automatically normalizing that stuff away. And then at the bottom end, it's making that slightly more important. But you still might want to clip that off in some way, because it might say, oh, this word that only occurs 3 times is very important, even though it's not something that you can derive any signal out of. So you might still want to set a minimum DF that kind of clips off the bottom portion, because it just expands your vocabulary and it doesn't really give you any significant signal. That's something that you just have to try. So like in the book, they were showing the grid search using the different regularization parameters. You probably want to do something similar with your TF-IDF in terms of determining what a good min-DF, what a good max-DF, and the various other parameters are there in order to get the best outcome you can.
I think one of the things that I took away from it was a lot of this is done to actually speed up the modeling process, right? I mean, if you had infinite compute resources and they could work infinitely quickly, you don't care, right? Mm-hmm. But this is one of the main points, because one of the points that they showed was, even though they used L2 and then they also used TF-IDF, it didn't really improve the results that much, but it did change the amount of time that it took to arrive at the model, sort of thing. So my takeaway was so that's one of the things. And the other thing is you just have to know your data. You have to look at your data and you have to see, like, do I have double negatives that are actually positive? And so how do I take that into account? Do I have rare words that I want to emphasize or rare words that I want to throw out? Because I may have rare words that don't actually really help me because it was some pedantic person who wanted to impress somebody else with their vocabulary, and it doesn't really help me. So I'm just going to throw it out. So I think so. They're the two takeaways I got from it: is improving your performance, your calculation speed, and you've got to know your data.
You kind of raise an interesting question, Stephen, which is, who is your audience? If you're talking about a lot of text that has esoteric words, a lot of academia has coined words, brand new terms, etc. So that's a lot of unique words. I think that it would be, in that particular instance, it'd be a mistake to just drop words because they weren't used very frequently. They would be very meaningful, yet unique.
You could only do it with a very, very low MinDF, like 2, because it would only help you on those 2 documents. And it's very unlikely to occur in your test set, or it's going to occur once per year, and if you have an equivalent of your test set every year, so it's going to help your model overall. Even though it's very important to a human, the machine has a very difficult time gaining that meaning from that word.
Yeah, if it had a dictionary and a semantic net, that would help, wouldn't it?
or a word-to-vec embedding of that word. But
all right, yes.
You got to build that. Yeah, either one would be great. And you're right, for those rare words. You're right. Sorry.
So the going back to the search example you were using, though, Hobbs, that is what is very useful there. If you have a word that only happens in 3 documents, it probably is a useful feature to be able to find their co-occurrence. So if you're looking on the web and you say this word has only happened 3 times, those documents are likely related if they have some similar jargon that is exceptionally rare. That's where TF-IDF really shines.
It's that exponential increase in your vocabulary, especially when you're working with n-grams. You'll have a lot of n-grams that occur in 3 documents, and you'll have a lot of n-grams that occur in 2 documents, and it's like billions. And so when you're getting out to that dimensionality, even these tricks of creating binary vectors, they can't help you. These binary search trees can't help you out of that level of dimensionality. So you have to draw the line somewhere for practicality.
So one of the, I think this might have been brought up last week, when you do count vectorizer and TF-IDF vectorizer, they're generating by default sparse arrays. And so an important thing to understand there that they didn't touch on here is your normal NumPy array. What it's doing is it's storing all of these numbers in all of their different spots. So if you have 0.47, 0.32, 0.11, for example, it's going to store the values for every single point in your array, basically. But when you do a sparse array, depending on the type, there's different kinds of sparse arrays. What it's actually going to do is it's going to tell you, so it knows we have 30,000 columns, only 10 of them are ones. It's more efficient to just say, here's where all of the ones are, here's the column, here's the row. It's more efficient to do that than say it's 0.0000000010000. And so there's a difference between a sparse array and a dense array. And the sparse array will take way less memory, but you might have difficulty throwing it into various different algorithms that don't expect sparse arrays. And the process of converting it to a dense array sometimes can make it balloon out to hundreds of gigabytes if you do it on a lot of documents or have a big vocabulary size. So that's just something technical that you might want to keep in mind.
And that brings up a good point about my technical limitation or the practical limitation on the size of the vocabulary. There is no limit if you use sparse matrices to hold everything. Then you can do all that stuff like fast search. And I imagine that's what Google does to account for those really rare n-grams and still find them.
So one of the things that they mention at the end, I don't have a great understanding of this, so I can't talk about it much, but they talk about the rank deficiency. My loose understanding of that is when you have a lot of values that are zero, it essentially eliminates that feature from having any power to contribute. So if you have, trying to think of this scenario, when you normalize it in such a way that only a single occurrence equals a zero, like when they were doing the log transform, that means that your model, if it's a linear model, can no longer make any contribution. So you think of the multiply that occurs when you do a linear regression. You can have a coefficient that's 500 or negative 500, and if the input value is zero, you cannot adjust the prediction at all. That was my understanding of their point. I'm not sure if that's the correct understanding, but that was what I derived out of it. Does that make sense? Did anyone have a different understanding of that section?
If you zero it out, you're blind to it. There's no doubt.
Hold on a sec, Ryan. I just want to check one thing.
And so not to complicate things, but on the flip side, if you are doing some sort of mathematical transform that turns your zeros into something else, then you can no longer do a sparse array. It greatly complicates things because now you have to store the values of every single row rather than, or every single column, rather than just saying, here's where the ones are, for example.
Yeah, so I don't know if it really has to do with zeros per se, but if you have if you have a lot of, you can talk about rows or columns, but let's just start with examples. Rows is easier. If you have a lot of rows, but the rows are not actually interestingly different, right? Then essentially you could have a million rows, but you might not actually have, how do I say it, a million different pieces of information. You might just sort of have 100,000 pieces of information being repeated over and over and over and over again. I mean, you could literally have duplicates, in which case that's the most extreme example of it's not really interesting information. And so that would be a case where like your rank would be more like 100,000, even though your rows is 1 million. And so you can have the case where things are literally that way, right? Or you can have it where it's close, and then that's still going to be a problem. I don't know if that at all answers your question or not.
So that what you described becomes a problem if you're trying to solve it analytically, right? So we're talking about linear regression. So if you're trying to solve it using, so they were talking about the I don't know.
Yeah, I mean, ultimately you're doing like a decomposition and inverse or whatever.
Yeah.
You know.
Yeah. So if,
but at the end of the day, it is a problem. So like in this case, you have more words in your encoding than you do examples. So there are more different words that appear in the vocabulary than there are Yelp reviews that they were analyzing. And so ideally, right, if you're trying to fit something, you'd kind of like multiple examples per feature so that you can, you have some signal there, right? And so what they're saying is that that problem is then exacerbated if in fact a lot of your rows aren't actually interestingly different. So now you have even fewer examples for the number of features, and so you're basically sort of underspecified, I think is what they were talking about.
Yeah.
And then you get into sort of this mathematical problem where if it's truly zero information, like in the linear algebra sense in the null space, then you could have any various multiples, plus 100, negative 100, whatever, on these various features, and it's not going to change your answer, right? But what's scary is if it's not quite completely zero, now you actually can take that into effect, and it just may be that the numbers are small enough that when it comes to your loss function, you're not really seeing much difference. And so then you can't tell the difference between the features that are actually really important versus the features that are just sort of doing this. And so essentially, I think they were saying that's how you get a bad model. And so regularization is trying to squeeze out the coefficients on these unimportant features. So I mean, this is really getting outside of feature engineering, but in terms of the regularization, pushes you towards smaller coefficients. And so essentially, if you have something that doesn't move things much either way, it's like 1/1,000,000th, whether you change the value of this particular feature, then you can afford to drive down the coefficient to towards zero on that, and it doesn't really change the result of your prediction. I thought it was kind of an interesting discussion. I was not expecting to see this discussion of sort of linear algebra and like solving problems, but when I read it, I tried to sort of take away the bigger picture and see that like, oh, this could still be a problem even if you're not actually using a linear model.
It's kind of interesting because they haven't really, they've very much glossed over models other than that one section about linear regression. And I think that it's kind of important to understand the model. I think they've just assumed that everyone is just using a linear regression all the time.
Yeah, so I tried to think about how this would apply in the bigger picture. So imagine that you are building, some tree-based model. Okay, so you got a random forest, you got a gradient boosting machine or whatever, and so you're at a particular place, and you are doing your splits. Okay, so imagine in one scenario you don't have this feature that's not terribly important, and so you have a bunch of values that are 5, a bunch of values that are 10, a bunch of values that are 20. And your tree's like, I can't really get much information from trying to split this. Okay. But let's say you throw in that extra feature, and now instead of having a bunch of values of 10, you've got 9.9, 9.91, 9.92, 9.93, so to speak. Right? So now you can just by chance say, oh, well, if I split it at 9.41, I actually have this, this differentiation, right? But in the grand scheme of things, that may not actually be providing you right? If you've got values at 5 and values at 20, the difference between 9.94 and 9.941 may be minuscule. And so it might not actually really be helping you for the bigger problem that you're solving. And so that's where, again, I mean, I don't know GBMs that well to know how they regularize these, but maybe there's just a certain amount of randomization and whatnot that tries to take that out. But so you could see then that if you threw, 1,000 features at this, then the odds of randomly stumbling upon something that looks like it's a useful split, even if it's not necessarily strong signal, that's where, again, it's not a linear problem, but you still could have that issue where something that's not actually adding a lot of value, the system could still be saying, oh, it looks like it's data and I'm going to try and do something with it.
It's kind of out of the scope of what we've discussed in the book, but I don't think that the GBM would. So the actual implementation of them, a lot of them have a setting that is the max number of bins. So if you have a max number of bins that's 256, I don't think that it would pick up the difference between 9.40 and 9.41 because it's limited to 256 bins. And if there's however many values, it probably wouldn't pick that up potentially.
Well, what I'm saying is that, like, if you took a real data set, okay, and you built a GBM and you got whatever your accuracy is, okay, and I know that smart people have worked on this, and so there's features in there that I don't know all the gory details, but if you took a really, really vanilla GBM without all the fancy features, and you said, here's this model, and I got, whatever accuracy, and then I just added 1,000 random number generated columns to it, what you would find is that just by the sheer number of them, when it's deciding splits, it's going to use those random columns in places that don't generalize.
Yeah.
Just by sheer numbers, some of them are going to happen to make what looks like nice splits. And so what I'm saying is, so then even if you're controlling for, leaf size and number of this and all of that, that even potentially very high up in binary splits, it's going to choose one of these.
Yeah.
And so that's where I think even in a nonlinear model, even in a tree, if you read the papers, they talk about regularization. They talk about how to over, with randomization and other things, like avoid those kinds of things giving you overfit data.
At the beginning of the data science bowl competition, Ken did a little study basically showing the different effects of adding noise columns and noise of different shapes and different I don't know how to phrase it, expressiveness, the number of unique values. And he saw that there was actually a strong, they get tricked fairly easily if you throw in noise columns and give them free cutoff points, basically.
Yeah, so I don't know if that was useful for everybody. But.
So I think looking ahead for next week, I just kind of search through the next 2 chapters. I think we could probably clear the next 2 chapters again. It looks like it'd probably be about 40 pages again. Talking about categorical variables and what else?
PCA, but I'm wondering if people are going to struggle with PCA. It's a pretty heavy concept.
Yeah.
So maybe we only do 1 chapter then. But the problem is that then it's a kind of a light chapter. So I don't know.
We could do 2 chapters, and then if people have problem with PCA, we could do it again the next week. So 5 and 6, and then it could kind of do 6, and then next week do 6 again.
Yeah, we can do that. Okay.
I'm fine with 2 chapters. What I struggled with was I didn't see anywhere, and for whatever reason, didn't recall that it was 3 and 4 this week, so I wasn't sure. Can we is there a place where we're posting our decisions about which chapters to read?
That's a good point. So I've only posted it in the meetup. I didn't post it anywhere in the Slack, Ryan.
You did post it in the meetup? Oh, in the meetup.
Mm-hmm.
Okay. Yeah, I didn't look there.
Yeah, and that's fine. So I think that's a good lesson. So I should probably post it in the Slack too.
Yeah, that's a good point. We can start doing that.
Okay.
All right. So I like that. So let's shoot for 5 and 6. And worst case scenario, we don't make it all the way through 6, then we'll revisit parts of it the following week.
Mm-hmm. So after this, we'll be doing the birdsong competition. And I don't know if you have any interest in talking about Omdena stuff, but if anyone has any other projects, we can talk about those too.
Yes, I would love to.
Awesome.
All right. That sounds great. And then actually it was really fun. Last week we had a number of people who talked about some other projects that they were doing, and also some people who were not part of the book club. So people who actually really did come on at 2 and who weren't part of the 12 o'clock group. So it's good.
Yep. So I guess we'll take a small break. Let's come back at, I guess, 2:05.
Let's come back at 2 for the people who are going to be joining us at 2 who aren't here now. And then I think if other people need a little bit more time to eat, maybe we'll just do a little bit of warm up. And so if you come back at 2:05, I think let's just try and set it up so that people aren't really missing anything if they want a little bit more time to grab some food.
Sure.
All right. Thanks,
Sounds good.
everyone.
Okay, bye-bye.